Hello, it is my great pleasure to welcome you to today's oral presentation session T4.3 on the topic of IT, power systems, and other enabling technologies. My name is Marian Jusko. I'm a seismic engineering officer with the IMS Engineering Development section, and I will be convening today's session with my colleague Klaus Johansson. Starting with the lessons learned from running the NDC in a box software suite in the cloud, followed by an overview of the next generation IMS Power System, with the session concluding with a presentation on containerized solution and optimized power supply system. All three topics will be presented via pre-recorded video sessions. However, all authors are with us online to answer any questions as they arise. So without further ado, I would now like to open the session with our first oral presentation on the lessons learned from running the NDC in a box software suite in the cloud, which has been authored by Mr. Gordon MacLeod and his colleagues from the Los Alamos National Laboratory, Oak Ridge National Laboratory, Sandia National Laboratory, Lawrence Livermore National Laboratory, and the Pacific Northwest National Laboratory. May we please start Mr. MacLeod's pre-recorded video presentation. Thank you.
Ladies and gentlemen, excellencies, colleagues, it gives me great pleasure to present the topic of SHI in the sky, benefits and pitfalls of NDC in the box in the cloud at SNT 2021. You may ask, why put the NDC in a box in the cloud? Based on some work done by Omar and Jonathan, where they've been doing some really large computing of seismic data within the cloud, and then my background dealing with the PTS and actually using the NDC box, which we called OSI in a box, during the IFE, it seemed absolutely natural to actually put NDC in a box in the cloud, and then that would actually increase the functionality and capability without impacting the infrastructure or bandwidth. So we set out to actually demonstrate what was possible. Our study was pretty straightforward. We wanted to basically place NDC in the box in the cloud and see if it worked, and whether it would work with both IMS and other data, and if that would actually cost more or less than what is currently being done. Bottom line up front, it works. We successfully loaded the virtual machine images from the secure web portal for both the SHI version of NDC in a box for, I think it was version 5, and then we also loaded onto that actually the version 4 alpha of the RN NIAB in the box. We were using fairly large machines in virtual space, and accessing them from pretty much our work from home places at home. And we found no noticeable lag while running the software from the various bandwidth environments. So not really meaning to, but what we ended up evaluating was 3 different setups of NDC in the box in the cloud. The first one we did was actually just a straightforward virtual box load into the cloud. Then the second one was building a Docker image and then using that, running that in a container. And the third was converting the virtual machine that's in SWP into an Amazon machine image. And we'll call those versions 1, 2, and 3. So version 1 was created by launching or creating an elastic cloud compute instance, selecting the Linux operating system, Linux operating system, and then installing VirtualBox using the standard YUM packages. So basically the OVA was loaded up into the cloud. And this followed, the release instructions from the SWP. The pros of version 1 were that it was literally, loading the VirtualBox right into the Elastic Cloud instance, and that made it, perfectly the same as what you would run on your desktop or your Linux box wherever it is. The real issue is that for this study we wanted to be able to make multiple instances and send those out for remote desktop environments, and we had real difficulty doing that, and so we moved on to from this one pretty quickly. Our next method was the Docker image, and we actually thought, because Docker is designed for cloud space, that this was going to be the way to proceed. And so we built a Docker file and then put that out, ran it using the EC2 hardware again in the cloud. So the pros were that because it's designed to be run in the cloud, it has much less overhead on it. Unfortunately, the Docker didn't support the system controls, so the graphical interfaces ended up being much slower, because we had to either use like X Windows or send it locally to the computer. So, the bottom line is that didn't work very well for the graphical images, but it worked great for the non-graphical capabilities. So third time's the charm, as they say. Version 3 uses the Amazon machine image as the operating system. We hit upon that after having discussions with our cloud team at LANL. Basically, you convert the VirtualBox OVA file into an AMI, and then install that into the EC2, and also install desktop virtualization software. So that worked really well. So again, that worked really well. The solution uses the VirtualBox as its basis, so it doesn't really change any configurations to support it. And then the virtual desktop software easily installed into the AMI, and the graphics worked as expected. The downside is that this is AWS specific, and really can't be moved to as far as we know, can't be moved to the other cloud providers. So we'd have to find a similar service in the other clouds. But this was our most successful, and the remainder of the talk is going to be just sharing what we found for each one of those pieces of software. So to make this work, we needed to have three things. One is the NIAB installation. We had to have in the cloud. We had to have virtual desktop software so we could actually use it, and then we had to have a way to update and distribute it to the users. And using the AMI piece of the software from AWS, we were able to do that. We ran the AMI on the Amazon Elastic Cloud Compute, or EC2 instances, and that allowed us to actually remote those EC2 instances out to people via email, and they were able to log in, run the NIAB software from that, and log in through the desktop, the DCV desktop that we used, which is the example above with the login. So to evaluate the AMI-based NIAB in the cloud installation, we launched 6 instances, each with 8 virtual CPUs, 32 gigabyte RAM, and 50 gigabytes of storage. These were sent out to evaluators at Los Alamos, Sandia, Lawrence Livermore, Oak Ridge and Pacific Northwest National Labs. They were able to log in remotely into each of their respective desktops for testing, and they were asked to use the software, the tutorials, and the documentation from the original version 5 image, and offer feedback on performance, software functionality, and the overall user experience. We later added in the RN NIAB software, which we'll talk to in a second. So we installed the SHI software in the cloud and sent it out in the instances. One of the things that, the first tool that was actually used was GeoTool. And it was, run through its paces. It worked well. There's no real detectable lag. The SeisComp 3 itself, just getting it set up has been a challenge to get it set up properly and working. And there's probably a couple of different issues. I think the biggest one is just getting the file structure set up so that the software knows where to go to get what files. That has been a bit of a thorn. But I have used the NDC forum and a lot of the capacity building tools to help check out the various systems. And as you say, it says, we recently had an Infrasound person become available, so we started testing out the GMPCC software as well. So as I mentioned earlier, we loaded the NIAB RN, I think this is version 4 alpha, into the SHI instance using Yum. And that meant that we were actually running it in terminal mode since we didn't have a GUI to click on. But thanks to Joachim's seminars and the recordings of those on the NDC forum, we basically utilized the NMS client, utilized Inspire, OpenSpectra. All those things really worked well. So it was, we're now trying to explore whether we can put other of the virtual machines into the same SHI network. So you may be asking, how much does this capability cost? Because we're spending 6 different instances, being able to send those anywhere, pretty much wherever your web browser was, you can run the software. What does that really cost? And for us, it ran roughly $14 a day. And that's because we had to keep the data up, which was stored on those virtual 50 gigabyte disk drives. We left them up continuously, so that adds to the cost. We're exploring methods to create a persistence data store in the cloud. That would basically mean that you could then spin up these instances when you needed them, not just leave them up all the time, because you'd be able to access the data. The other thing is that, again, this would be, we had fairly large machines, 32 gigabyte RAM and 8 CPUs and 50 gig hard disk space. I kept wanting to make it into a non-virtual piece. But the thing is that we'd be able to right-size those for what would be needed, and that may also reflect in the cost overall. So bottom line is it's not really, really expensive to do this. Our initial conclusions for the AWS NIAC using the AMI, it worked well. We were able to set up software and access to the data that are identical. You can actually troubleshoot. There's kind of an added benefit of being able to access it from anywhere. And if it was something that this PTS was supporting, you could actually email it to the support desk, and they could actually investigate what was your problem within your instance while you were on it. The things we're still investigating is the need to set up multiple AMIs to match the VMs. You know, as I noted, I actually loaded the RN NIAB into the via YUM into a VM that was already set up. I haven't done that for GrandSim or WebGrape, but otherwise you would end up with multiple AMIs for each one of those to set it up, which is really how they're set up for from the secure web portal. And bottom line is that this works great for AWS, but what, you know, we need to know what we can do with the other cloud providers. So with that, I guess ready to take virtual questions.
Well, thank you very much, Mr. McLeod, for the very interesting and informative presentation. With NDC in the box, widely used in our community, both inside and outside of the PTS, it's really wonderful to learn more about all the efforts vested into exploring its capabilities to run in the cloud environment and without the dependency of a physical hardware. Do we have any questions?
Don't have any questions.
We don't have any questions
in our pipeline here.
Okay, maybe I can ask one question since we still have a few minutes.
I have a question too.
So I guess my question, you mentioned on one of your slides that Linux CentOS is used as the underlying operating system to run the NDC in the box in the cloud. However, with CentOS on its way out, I guess the question is, how will you approach its feature compatibility with the operating systems which will be supported by various cloud servers and environments?
Well, it's really going to depend on really what the PTS goes to. I don't know that it makes a lot of sense to go to a different operating system than what you're using for the NDC in a box. But yeah, it's you can set this up very straightforwardly. It's sort of like a plug and play where you're when you're setting up the AMI, you can just basically decide, the Elastic Cloud Compute, you can decide what software you want to put on it.
I see.
So it's very straightforward.
Okay, thank you for that. And I just a very quick follow-up question. On your closing slide, you mentioned the need to investigate the capabilities with other cloud providers. Do you already have some specific candidates in mind?
Well, probably, you know, the obvious choice would be like Azure. I mean, there's also Google has some and stuff like that. We haven't, because of the contracting mechanisms and stuff like that, it's going to be a little bit of a bigger lift for us. We already had AWS in place, so it was easy to use.
Okay, great. Thank you for that. So since time is of the essence, I think we will now move to the next presentation on the next generation IMS Power Systems. Thank you very much again. It was wonderful to hear your presentation. And may we please start the pre-recorded presentation.
Hello, my name is Marian Jusko. I'm a Seismic Engineering Officer with the IMS ED division at CTBTO. And I'll be sharing with you an overview of our next generation IMS Power Systems we seek to deploy throughout the international monitoring system to strengthen IMS stations' resiliency to catastrophic failures, which often arise from power-related issues. The introductory slide picture captures the essence of what we envision the new power system platform to be like. In short, the platform needs to be highly flexible and is designed to support integration of multiple power sources, depending on what's feasible at any given location, but also facilitate flexible exchange of system components, which might be required to adapt the power system to site-specific environmental factors and system loads. The project's focus was therefore on the design of the power management system to bring both of these requirements together. So let's have a closer look at what these design requirements entailed. Well, first and foremost, we wanted to put a strong emphasis on the importance of market research and vetted component selection. In the project's initial phase, we focused on established vendors, which employ strong quality control and quality assurance practices throughout their supply chain. In addition, we wanted to ensure that the selected system components have a history of reliable operation in similar mission-critical applications such as military or telecom. All of the components which went into these power systems also had to comply with environmental specifications, specifically operating temperature range from -40 to +60 degrees Celsius. It was equally critical to ensure that these new power systems provide clean, uncompromised data quality within the 0.02 to 100 Hertz frequency band, which is shared by IMS SHI stations. And this is something that was directly incorporated into the factory acceptance testing. Although the new power systems were meant to be flexible, they also need to introduce baseline uniformity across all use cases. And this was achieved through modular design, where pre-allocated space was reserved for various system components. Aside from promoting flexibility and uniformity, it also allowed us to make any ad hoc on-the-fly component substitutions. So, for example, to convert one power systems from primary AC power source to a PV power source is simply the matter of swapping out the charge controller modules and other components, but without really affecting the overall system design. Perhaps the most critical design requirement was to ensure that the new power systems feature fully automated switchover between primary, supplemental, and backup power sources, and this is utilized through the use of smart network devices. They often run at very remote locations, which are often unmanned, and therefore this is a very critical design requirement. We also didn't want to restrict the new power systems to only existing technologies, and wanted to make sure that any new technologies coming on the market can be simply plugged into these power systems. In the current form, the IMS power systems already support fuel cell systems. They make use of smart chargers based on MPPT technology, and they also support battery banks of all battery chemistries, including lithium batteries, and make use of smart devices, which often support API interfaces. The modular design, therefore, gives us a high degree of flexibility where we can order or deploy these power systems with the optional remote I/O control or even the backup failover communication link. We can also deploy these in a wide range of form factors and enclosures of different IP ratings, of different finishes, including stainless steel for marine climates. They can be insulated if need be. Since we wanted to make sure that these power systems can be deployed anywhere throughout the IMS network, it was critical that the system can be fine-tuned to site-specific system loads and environmental conditions. So, for example, in the case of PV, for locations with a low solar insolation during winter months, it was critical that we can scale up the PV array and support up to 6.4 kilowatts of PV. The hybrid power systems support up to 600-watt supplemental power sources such as wind power or thermoelectric generators. And again, they can coexist with battery banks of varying sizes and chemistries. And finally, to ensure these systems can be deployed quickly and also to mitigate any installation errors, we make use of the modular subassemblies, keyed connectors, and pre-assembled cable harnesses. Well, given the large number of different station configurations within the IMS, where final permutations depend on the type of telemetry, sensing instrumentation, and data acquisition system, it was necessary to consolidate and group these many configurations into tiered but well-defined categories. The IMS power systems were therefore categorized by system load and environmental requirements into the following power system platforms and categories. The remote station power system platform, consisting of category 1 power systems which support loads up to 40 watts and represent most IMS SHI stations without the global communication infrastructure equipment, and a category 2 power systems which support loads up to 200 watts and mostly represent auxiliary seismic station with GCI equipment. The category 3 and 4 power systems are meant to represent power systems for the central recording facilities and support loads up to 10 kilowatts and beyond. And category 5 power systems are meant for polar regions and feature hardened components to withstand these extreme polar climates. As of today, design and factory acceptance of the remote station power system platform has been fully completed. So let's now have a closer look at the remote station power system platform. The physical interface of the remote station platform has been designed to emphasize flexibility and modularity. Omitting the power generation equipment, the platform consists of the following three physical modules. The power input core surge protection, which prevents large power surges, such as lightning, entering the structure housing the sensitive power system components. Then we have the battery bank. And lastly, the power control panel, or PCP for short, which is really the brains of the power system and manages the main power system functions. Any external components just plug in and coexist with the main building blocks, and any changes of the input power sources are handled through fine-tuning or exchange of components inside the PCP, but do not require overall system redesign. I also mentioned that the next generation power systems all provide filtered 12-volt DC as well as 24-volt DC power output to facilitate interface with new generation as well as old legacy instrumentation, which is still used throughout the IMS. So let's now have a closer look at the power control panel. The power control panel, or the PCP for short, is contained inside a single enclosure, which is adapted to site-specific needs. All of the components are DIN rail mountable in a pre-allocated space with clearly defined functions, with areas dedicated to primary power, supplemental power, the battery bank, the output module components, the charge controller module, and the optional remote I/O monitoring and control. The PCP can be packaged in different form factors, from pole mount, wall mount to chill style enclosures, and they all feature high quality stainless steel cable glands and pressure vents. So here's a more in-depth schematic of the power control panel. To demonstrate the flexibility of the platform, the system adapts to the varying input power sources simply by free interchange of the charge controller module. So for example, a single phase AC power systems would utilize the Delta Q IC650 charger. If we have a larger category 2 system, we would simply substitute the Victron Skylight TG, which also accommodates 3-phase AC systems. And for PV-based or hybrid power systems, we have the capability to utilize the TriStar MPPT charger. And for larger input power sources, for PVs of up to 6.4 kilowatts, we simply install additional chargers in parallel. All chargers are smart chargers and support all battery chemistries, including lithiums, and have a rated operating temperature range usable down to minus 40 degrees Celsius. So let's now have a closer look at the power control center. So the Power Control Center, or the PCC for short, facilitates a remote state of health monitoring and remote I/O control, and it provides alert notifications in the event of system faults or pre-configured SOH threshold crossings, which is a key in operating mission-critical networks. This is achieved through the use of Control by Web X600M I/O controller and the X16 and X17 analog and digital expansion modules. It is highly modular, scalable, and can be easily configured through a web-based built-in web server. The Power Control Center also features a low power consumption DC Ethernet switch, which then facilitates interface with other smart devices such as the charge controller module. For added redundancy, the optional Iridium-based ZIAST short burst data modem can provide backup communication path in case of unexpected outages of the main communication link. So as of today, 6 IMS power system types have been designed, tested, and are ready for deployment at any IMS SHI station, regardless of its location or input power source. Each of these power systems can be ordered in 4 variants, depending on the need, which essentially results in 24 permutations to cover all use cases. And this includes all power systems spanning from a CRF supplied DC to power systems with a native AC power input, PV input, or hybrid systems with a PV power as the primary input. So here's an example of the hybrid power system with a PV primary power source utilizing 2 TriStar MPPT 60M charge controllers, which interface with a PV arrays of up to 6.4 kilowatts. And this particular system also makes use of a supplemental power source provided through the horizontal axis wind turbine. This particular system is also configured for 48-volt battery bank and comes in with the remote I/O control and a optional ZIAS Iridium-based failover communication link. So here's another example of a Category 1 hybrid polar power system, which will be installed at PS35 station in the Russian Federation later this year. It's a PV-based power system connecting to 2.4 kilowatt PV array and utilizes two battery banks. The main battery bank is a lithium-based rechargeable battery bank of 3.2 kilo ampere hour capacity with an integrated battery management system. But the system also uses a secondary non-rechargeable battery bank with automated failover, which is used essentially to bridge over any unexpected power failures. The system also supports remote state of health monitoring and air control and utilizes 48-volt battery bank to mitigate resistive losses. All of the power system variants since underwent successful factory acceptance testing, with each power system subjected to validation of assembly, basic operation, as well as operation maximum capacity. Reliability testing was also part of the type approval process, as was the data quality testing, where each power system was actually used to power a reference seismic and infrasound equipment. And the type approval of each power system variant resulted in the issuance of a certificate of conformity by Electrical Safety Authority. In addition to the factory acceptance testing, which was conducted in controlled lab environment, we've also subjected the new IMS Power Systems to field conditions, where two of the power systems have been deployed at some DS FACT sites in January 2020, where they continue operating reliably for over 1.5 years now. And we have another test planned for polar-like climates, where we intend to deploy the hybrid PV wind power system at a remote test site in Alaska later this year. So in closing, here's an overview slide detailing the project lifecycle. The prototype phase has now been fully completed, with all power system variants successfully passing factory acceptance testing. The long-term field testing at FACT is ongoing, and we, as mentioned on the previous slide, intend to have another deployment in polar-like climate in Alaska later this year. All lessons learned and system fine-tuning was directly incorporated into the life cycle and also into the production of any new and future units. As of today, we're in the production phase, having the capability to deploy any of the next generation power systems and order these from a number of running contracts. And to date, we already deployed some of these systems at ICE 51 Bermuda, at PS26 Niger, and we have another deployment planned later this year at PS35 station in the Russian Federation. As for next steps, we are working on a release of IMS Power System guidelines, with a final draft already completed and official release planned for July 2021. And we, in parallel, always look into incorporation of new technologies for further improvements. In the next phase, we're going to look at the turnkey solutions for Category 4 and 5 power systems to address the needs for the central recording facilities. With also an aim to promote these systems as viable candidates for powering radionuclide stations as well. And this brings us to the end of the presentation. Thank you very much for your time and attention.
Okay, do we have any questions that came through?
Not from the chat, no. Yes.
Okay, so I guess I propose we should then maybe move to the next presentation, and time permitting, maybe at the end of the session, after the third presentation, maybe some questions will come through, and then we can maybe address them at that time. So I would maybe now like to give the floor to Mr. Leopold Rion of EnviroEarth, who will share with us his pre-recorded oral presentation on containerized solutions and optimized power supply systems. And maybe please start.
Welcome to my presentation about containerized solution and optimized power supply system for the EMS network. I am Leopold Rion and I am working at EnviroEarth. Before beginning, I just would like to say that I am really happy, and actually at EnviroEarth, really happy to participate to this year edition of the SNT, not because of its particular format, but because 2021 is kind of particular for us, as it is the 20th birthday of our company. And indeed, since the beginning, since 2001, our company have been involved in its own way in the improvement of the EMS network. So today, what I would like to do is share with you the fruits of this 2 decades long collaboration with CTBTO by presenting you 2 of our main activities inside the EMS networks and beyond, which are the supply of containerized solutions and power systems. So as I said, Andreas is involved into the EMS networks since its beginning, since 2001. And basically, what we do for the EMS network is the operation, installation, maintenance, and upgrade for many stations of the network, as you can see on the map. But we have also another division which is focused on the supply and design of PV turnkey system and hybrid system with PV arrays, mainly for industrial facilities, villages, and hospitals in emerging countries. You can see here some pictures of our most recent projects inside the EMS network. And on the right, now appearing what we have done since like 7 years in the renewable energy field. If we go back to the EMS network, I think we can say that we have 5 major sectors of activities, 5 ways of working inside and for the sustainability of the EMS network, which are first, operating station with post-certificate activities. We are actually operating 4 stations in 4 different countries, in Tristan da Cunha, Saint Helena, Cabo Verde, and Mauritania. We are also supplying wind noise reduction systems and reference systems for Infrasound stations. If you want to know more about this subject, you can consult our e-poster, which is part of this SNT conference. We can also supply communication system for intrasite communications, and it declines in optical fibers, copper wire, wireless system, and more recently, cellular system and very small aperture terminals, which is satellite communications. We can also provide enclosures, optimized enclosure and modular enclosure for hosting the equipment, but also containerized central recording facilities. And at last, we are also able to provide design and manufacturing of modular power system protected for remote site and CRF. Everything that I will be presenting today is the result of a long-term, close and constant collaboration with CTBTO. And today's focus will be the power system and the enclosures that we can provide and we have been providing for improving the EMS network. This picture shows the very first bigger solar array that Andreas has installed, and which is in Tristan da Cunha, same island as we are operating the monitoring station for the EMS network. So I think the photos is a really good transition to the main subject of today, which is presenting a containerized solution and optimized power supply systems. So we are happy at Enviros and really pleased to keep on supporting CTBTO in its upcoming challenges, and mainly in the standardization of its power system throughout the EMS network. And actually, thanks to the combined knowledge and know-how of our 2 sectors of activities, which are monitoring and energy, we have been able to develop a power system platform which is in line with the IMS Power guidelines of conception and standardization. The power system architecture we present today is modular and autonomous, but also innovative by allowing to install new technologies in the EMS network, such as lithium-based batteries, fuel cells from methanol mainly, and also wind turbine, horizontal or vertical. The two main focuses we will have after this slide is first the power enclosure and then the energy monitoring system. First, we know that some faulty or bad material and components may cause some on-site struggles and critical losses of data. So this is why we have included in our quality process the following procedures. First, performing on-site assessment and factory acceptance test, power cutoff scenarios for new power system solutions, and checking the reliability of our equipment. Second, in our facilities in France, we have the ability to conduct research and development studies in order to characterize the performances of new equipments, technologies, of prototypes that may arrive in the future, and to see if they are properly they are the proper specification to be implemented in the EMS network. And in line with this research and development capacity, we are currently developing our own local bench test at our facilities, where we will be able to test our new Windows reduction system prototypes, power system, communication system, of course, volts, and the interoperability between all these pieces. Speaking about volt, you can find here the different kind of enclosure we are offering to improve the EMS network. From the lightest, the peddy case, to the heaviest, the heavy-duty stainless steel volts, which is like a war machine, more like the most secure, the most rugged, and the heaviest solution we have. But one may wonder how to choose the best enclosure. Well, it depends, of course, on the field of research, the battery technologies, type of operation and maintenance, and at the end, but the most important, the station environment. To adapt to the station environment, all our solutions are highly modular. As you can see in this slide with the presentation of every customization possibilities we have with the stainless steel rugged enclosure. To an example of how it looks once installed, here is the last project we did in IS-47 South Africa. And we got, for the record, we have also installed this solution in some other places in Argentina, Russia, and Antarctica. Now, let's talk about the power system monitoring solutions. So, same for the volts, our power system solutions offer the possibility of customizations and to add options to the system. One of them is adding a state of health monitoring device in order to have access to, for example, the real-time data monitoring, the access to history and details, control parameterization control and parameterization console to set up alarms, and for some versions, for example, the color control GX, which is presented here, wireless access via Bluetooth, and with the optional transceiver, remote access via web interface. Actually, we have installed some of these color control GX devices in some of the EMS network stations. For example, ES41 on the left in Paraguay and IS1 and 20 in Zimbabwe on the right with the transceiver, as you can see. Now, just to give you an example of what can be done with this kind of device, I just want to share a former project we did a case study actually in Mauritania, which was the installation of a hybrid system for the UNFPA office. The specification, without going into further details, are quite equivalent, quite close to category 4 power system I asked for a central recording facility that is requiring less than 5 kilowatts. This is an overview of the dashboard you have on the remote management application or web console of Victron, which gives you access to all the current information of your system. For example, the state of the inverters, the PV consumption, the solar production, sorry, but also the state of charge of the batteries, and you may also have access to a lot of other information of the historical data. As I said before, for example, here I presented the state of health of the battery for, I think, 1 week. So now I have finished my presentation. I would like to thank you for your attention. And I also would like to thank the SNT team to being able to do this event despite of the circumstances. And of course, looking forward to answer to your questions.
Okay, thank you very much for the nice presentation, Mr. Rion. It is really nice to see the large variety of containerized solutions you have, which can be pointed for the vastly varying climates encountered through other IMS. Not sure we have any questions.
We have one from Ben Katas, and it's a question to Leopold about how sustainable solutions can be, or how it is part of the new design. I don't know if Leopold can go into a few details about that, maybe from experience or from earlier designs, how the new boxes or new equipments that you present is improving the sustainable design for the future.
Yeah, for example, speaking about vault solutions, the containerized solution in order to work the equipments and power equipments or sensors. If you are, for example, in a sensible area where there is a risk of theft, for example, or any other kind of risk, like hiding, for instance, as I presented in the PowerPoint, the anti-theft system can improve the sustainability of the stations because it will be more resistant to any risk of accessing the inside and, for example, the batteries.
Okay, thank you for that. I actually have a follow-up question myself, and I'd like to hear more from you to learn what drives your decision process and actually the design process itself to point the most suitable materials and the amount of added protection, such as insulation, to optimize the containers for site-specific environments. So do you start by collecting the meteorological data sets, which are representative of the year-round climate data, such as the minimal annual ambient temperatures, and you start your design process to make sure that the system adapts to the worst possible conditions, or just like to learn more about what your process is?
Well, first, the design process, designing a new solution is always made with in line and in constant communication with the CTBTO. So it's an exchange in order to progress to the best solution. For example, first we like to have the opinion of the station operator to see what will be the most adapted solution, and then when you're speaking about thermal studies, how do we configure the thickness of the insulation layer? It's first by doing a model of implementation, taking into account the solar radiance, the temperatures of the place of installations, in order to figure out what will be the best thickness of insulations in order to resist, to offer the best atmosphere for the inside of the vault of the enclosure, for the equipment in order to reduce the gradient of temperature. So the first thing we do is thermal study, modelization of the vault in its environment of implementation, in order to decide what will be the best the thickness and also the best material in order for this installation. Yeah.
That's great. Thank you for sharing that. I think we actually have a question.
Yeah, so
may I ask you to read the question?
Yes, there's one from Sean Ostrovsky. If you sort of already reply or answered this question, if how you do manage heat management, if do you do any implementation of heat pipes? And while we're at it, we're running a little bit low on time. So Gordon McLeod has a question on how do you decide which battery to use?
Can you repeat again the question, please?
Yeah. How do you manage heat management? Do you have any comment on that besides what you'd already said?
Yeah, heat management.
Yes.
Yes. So well, it depends of the case, of course. For example, we can talk about ongoing projects that Marian spoke about in this presentation just before in Russia in PS35, where we, because of the thermal study, actually we are adamant on putting some kind of resistance in order to heat the battery enclosure. So this is taken into account when we are designing at the beginning the best configuration for the equipment.
Okay, that's great.
Thank you.
Thank you for that. And I think we also have one question which came through for the first presenter.
Yeah, we have a few.
So Mr. Gordon McLeod, I don't know if you're still with us. There was a quick question.
He is, because he also asked which battery we decide to use. We'll return to that maybe.
Yeah.
But Jonathan McCarthy asked which AMIs you can choose the operating system you install into. So I think Marian asked something about operating systems already, but I don't know if I'm restricted to any of these.
No, so Jonathan was one of my co-authors. He was actually answering Marian's question. So basically, you can select whatever operating system with the AMI. So you can basically, there was the point and click comment that I made. So he was just trying to help me out.
Okay, perfect.
And then Xavier from OSI, he reached out to you to stay more in touch about this, because I think it's very beneficial for OSI, or he says so at least.
Yeah, I was actually more targeting NDCs, but you know, if the OSI division finds it useful, that's fine too. So
I actually have one question I was wondering about the cloud. Do you have any comments on the network usage? How strong a network connection do you need? Because to my understanding, sometimes it's quite a lot of data that you're pulling in and out of the databases in the NDC in a box.
well, so that's the beauty of this, is that's all done in the cloud. So it's basically you're just using the web browser interface for the GUI, and then everything else is in the cloud. So we're basically taking the data from the IMS to the virtual machine, and then that's basically on the bandwidth pretty much between Amazon and what the PTS has. So it eliminates a lot of that up and down from that would be to through your local bandwidth. So one of the slide things I mentioned was we were working from home here in the United States, and so we have a variety of bandwidth in our houses, and we didn't see anything that affected us. So
thank you very much for that, Mr. McGregor. So my understanding is that the room needs to be prepared for the next session. So with your permission, I'd like to thank all presenters, authors, and co-authors. I also would like to thank our technical support colleagues here for the session. And as for the viewers, please feel free to post any follow-up questions on the S&T Q&A platform, as these will be then reviewed and passed on to the authors for follow-up responses. So again, thank you all again for your attendance and participation. Thank you.